I just got in the door. I've been thinking about what I said before about space being simply the distance between things. I questioned it. And these are some thoughts that have come to my mind since then. Got a lot of different thoughts. I'm not even sure if there's a conclusion to this. But I don't even know if I'm saying this in order, but there's one of the things you could think about is say if space, or what they call space, or the universe, what they call the universe. Let's say it was just one square, a square. Now this is a two-dimensional universe. Right now we're going to concentrate on two. All that existed, if all that existed was a square. Now what do you have in your mind? What are you imagining? You're imagining, right now most likely you're imagining a blackness with a square in the middle. And that's not true. Really, that's what's the word? That's inaccurate. If this square was the universe, or if this square was all that was, it would be the universe, what they call the universe. The universe would be a square. There wouldn't be any blackness on the edges of it. It would be all that there is. So if you were to draw it on a paper, the paper would have to be square, and the paper would represent the entire thing. And then it's almost like the edges of the paper would be the edges of the universe. Like if somebody lived in this universe, they wouldn't know that the edge of the universe is actually the edge of a paper, and then there's a human holding the paper. But I'll leave that up to the movie makers to talk about, because I don't believe anything like that. Let's see. Okay, yeah, all right. So if there was nothing but a square in the universe, or if that's all existed, it's redundant to say that's all there would be. But there wouldn't be any space. And by the way, that square you're imagining, are imagining, what color was it? Because there wouldn't be any color, because color represents the different wavelengths of light. One could argue that the square would be, what color would the square be? One could argue that it would be black, which is a representation of no light being reflected off of it and going into your eye. But what's your eye doing there? Because you wouldn't be there anyway. So could anything really exist anyway if there was no one there to perceive it? If a tree falls in a forest, does it make a sound? So anyway, what color would it be? Just imagine, I suppose, that it's whatever color you want, but really would be black, but actually wouldn't be there at all because there's no one to perceive it. Anyway, okay, so there's this square in the universe, or it is the universe, and there's nothing. Okay, nothing else. There wouldn't be any space. The only way space can be is if there were two squares. Let's say there's two equal-sized squares side by side. Now the equation changes. The distance between the squares becomes space. Space, in my opinion, can only exist if there's more than one of something in the universe. It could be argued that if there was only one thing in the universe, there would be no space. Now someone could say, oh, well, there's space between the particles that make up that thing. If we're saying that there's only one thing in the universe, then it goes without saying that that is the particle. That is the particle. Okay, and then that tests your belief of whether you can believe something can exist that's completely solid. Can something exist that's completely solid? For the sake of just imagining, we'll say that there is. The two squares, side by side, equal size, and they're side by side, and the distance between them is space. This is a two-dimensional rendition of the universe, so we're not going to get into the third dimension yet. And my lack of attention to the idea that there's a third dimension when I first gave the definition that space is distance is what that's what brought on all these thoughts. So there's two squares side by side. The distance between them is space. We have no way to measure this. What's the distance between these two squares? All right, can you say an inch, 2 inches? You can't say that because a ruler, or I should say, rulers, inches on a ruler that we know of are all that distance that we define as an inch is a comparative distance. And I'm saying this by common sense, not by knowledge. I'm just saying the only way I can understand this, that there would be a ruler with an inch on it, is that someone somewhere, that this distance that they call an inch has to be compared to something. You can go to another ruler and check to make sure that that inch is indeed an inch. Like if I asked you about you told me, you pointed to your ruler and said, this is an inch, and you're pointing to the inch mark, the inch line, and I said to you, well, prove it to me. You would go and get another ruler somewhere and hold it up to that ruler. And if someone came along and said to us, prove to me that that's an inch, I suppose we would go somewhere else. We would go to wherever and buy a ruler and hold it up to that. Now we got 3 rulers, one by the other, and we're looking at the inch mark, and it says an inch and an inch and an inch. And someone comes along and it goes on, and we buy another ruler and it says an inch. And if you buy an older ruler, you go back in time, if that were possible, and get another ruler that says an inch. Somewhere, someone started this idea of an inch. I'm going to guess that I think a ruler is 1 foot, so maybe that represented at one time there was a guy with a big foot. Well, maybe back then it was considered average, but where is he? He's gone now. We don't have his foot anymore, so we don't really know the only way we know is what a foot is because we got these rulers. And then we break it down into 12 groups or 12 sections, and they become inches. So that I'm going to guess that's, I don't know if I was told that in the back of my mind, if I'm getting that, or if I'm just imagining this at this moment. I don't know. But anyway, it makes sense to me. But wherever we got this idea of a foot or inches, my common sense tells me it's all comparative. It's got to be compared to something. And then you can say about that thing, well, okay, we got the inch from this, or we got the foot from this thing, which is a foot long because we looked at it and defined a foot by it. Okay, how could you define how long that thing is? The thing that it was, the thing that was the standard for that. How do you measure that? That existed before the ruler did. Okay. And I say, well, it's as big as this. Okay, how did you measure that? Well, it's as big as this. How did you measure that? It goes on. So for this reason, I believe that all measurements are simply, all measurements of distance are comparative. Now back to the 2 squares. There's 2 squares side by side. That's all there is in the universe, or that is, no, I can't say that is the universe. Well, I can't say one of them are, and I would say that the universe, now that there's 2 squares, now this distance is the word universe from one of the squares, because now there's more than one part to the, it's almost like it lends some credibility to the need to come up with a word. So now that there's 2 things, we'll call the entire thing the universe, whereas it seems silly to call a square the universe. It seems silly to call 2 squares the universe, but maybe slightly less silly. 2 squares. And there's a distance between these squares, but this exists before we invented rulers, so how do we measure the distance? What's the distance between these 2 squares? Is it a foot? Is it a yard? Is it a mile? Is it 200 miles? Is it 2,000 miles? Is it 200,000 miles? Is it 200 million miles? What's a mile? There is no way to express the distance between these squares. It could be anything. It could be as close or as far as anything. There's no saying what the distance between these 2 squares is. But there is one way to express it, and that is to compare it in relation to the size of the squares. That's right. If the distance between the squares, maybe the distance, let's say the distance between the squares is half the distance across either one of the squares. Now you've got a reference. You're using something that exists in the universe as a reference for distance, which I would call space. or if someone asked me what space is, that's what I would say it is. It's simply a measurement of distance between something or some things. Okay, and an interesting point is that if only, going back to one thing, if only one thing existed in the universe, there'd be nothing to compare it to, or no space to compare it to, which is another way of saying there'd be no nothing to compare it to. And then who, if that were the case, who would be the one to say whether that's space or matter? Is it matter? Or is it space? If it was solid, if it was not made of particles, it almost comes full circle again, and it becomes the same as space. If there was only one particle and it was completely solid, it's almost like another way of saying nothing, because there's no reference to compare it to. There's no solids to compare it to. Anyway, so two squares. The only way to measure going back to saying the only way to measure the distance between the squares is to compare it to the size of the squares. And I got some of that idea, I think, from if you get real close to something, and then you start backing up. Let's say there was two squares, and you had your face right by it, and then you started backing up. That space seems to get smaller, but as you get closer to, if you were to get closer to it, that space can look very big. So without comparing it to the size of the squares, that space could be anything. So anyway, two squares right next to each other, the space between them, the distance between them is what I would call space in the universe, or whatever you want to call it. Okay. Two-dimensional. Now let's say if you were to change that, let's say there were two circles. All that there are in the universe is two circles. Now this changes things because the distance, previously the distance was constant. At any point along the continuum, along the contour of the inner contour of these two squares, the distance between the squares is the same. I also find it interesting that the distance between the squares is a constant. It's always in this case, half the distance across the squares. However, if it is true that if there was only one square in the universe, it would be all that there would be. Then saying if there were two squares in the universe, with a certain amount of distance between them. I think as soon as you make two of something, changes things in a specific way. Having only one of something, there's nothing to compare it to. So any distance, any measurement of its size is both infinitely large and infinitely small. This is all theoretical. This is mind-bending stuff. In a way, it's almost meaningless to say, but I don't know, somehow I feel like it's useful, or that it'll lead to something, or for some reason it's curious. But it's true that if there was only one thing in the universe, and it was a particle, and it was completely solid, it would be simultaneously infinitely large and infinitely small. Right? Now, let's say we're going to make two of these things. It is no longer infinitely large and infinitely small. I'm incorrect about that. I think that if there were two of them, and one was larger than the other, then they would both cease to be infinitely large and infinitely small, because one is larger than the other, one is smaller than the other. However, going back to my model of them being the same size. I'm incorrect again. I was about to say if they were the same size, then they would be both infinitely large and infinitely small, but I'm incorrect about that because there's another distance to compare to, and that is the distance between them. So as soon as you make two squares instead of one, size exists. Well, size exists. Was there more to that? Yes, and distance exists. Size and distance exist. And one could argue that time exists because unless they were made at the same time. If there was first one square and then another, then time exists, and that would be the time that elapses between the making, between the existence or appearing of one and the existence or appearing of the other. Time would exist. Now, how do you measure that time? It's the same thing as size. You would have no measure for that time. Was it seconds? Was it how many seconds? Was it a minute? How long elapsed between? The only way you can measure that time is by comparing it to something else, and since nothing else ever happened, in a way, it could be true to say it is an infinitely long amount of time, and in a way, I suppose, no, I don't know if you could say it was an infinitely small amount of time. I don't know if you could truthfully say that. I'm going to leave that one. I'm not sure what to say about that, but I do believe that it is infinitely large amount of time would have elapsed in a way because there's nothing to compare it to. There is no reference, so that could be seen as large as you want, or as small as you want, barring the idea of no time at all, which could be argued not to be time. So I'm going to leave that one alone. I don't know what to say about it. Okay, now we're changing the model from these squares to the circles. Now in the previous model, with two squares in the universe, being the universe, the distance between the squares was equidistant at all points along the continuum of the the two sides of the squares that are facing each other. All right. Now we're going to change that by changing it to circles. I chose circles because it creates an interesting situation now. A circle is sort of a hypothetical shape. I don't know how to express this, but let's go back to the square model. With the two squares next to each other, there's two faces of those squares that are facing each other, and at any point along that line, those two lines that are the sides of the squares facing each other, there's an equal distance between them. But now we're going to, before I say this, let me just change this model. Instead of that, we're going to say, no, that's not a good model. Let's say that instead of being squares, hold on. Let's say if you were just browsing the inner continuum, let's say you were just looking along the line of one of those squares, of the edge that faces the other square, and somewhere in there was a divot, a square divot. In other words, the line would go inward, the edge turns in, goes a certain distance into the square, goes up a certain distance, and then goes back the other way to the right. I'm imagining that the thing goes left, up, right, and then continues going up. This is a, what's the word? This is a tangible, this is a quantifiable, it, the, the, the duration, how can I say this? If you're traveling along that line at a given speed, the amount of time that the distance between where you are and the edge of the other square changes is quantifiable. It because that divot is measurable. It's a certain distance. So that change is measurable. However, if that square were a circle, the traveling, and I don't even know if I could say that. The moving from, imagine two circles next to each other, and you're moving from the bottommost point where a distance exists between the two shapes to the topmost point where a distance exists between the two shapes. It is in a permanent state of change. In other words, as you're moving linearly from the bottom to the top and you are measuring, you can measure the distance between these two shapes at any given point and get a different answer. That's why I say that a circle is, in a way, it's incomprehensible. The concept or principle of a circle and the principle of infinity are inseparable in a way, because you see what I'm saying. Because if there's two circles next to each other, I don't know how to explain this any better. A constant curve means, in a way, there's an infinite amount of points, you could say, in there from which you can measure. And since it's a constant curve, no matter how small of an increment you change your vertical position, there will be a change in the distance between these two shapes. Okay? I don't know if I've explained that very well. I know these things, but it's just, sometimes it's extremely hard to say it. Okay, so that's a two-dimensional model of the universe, what they call the universe, and the universe consisting of two circles. Yeah, so in the circle model, the distance is constantly changing. Now we're going to move on to the third dimension. Let's imagine that the universe were two cubes. The answers would, the same things would pertain to the first model, except for now we've got this business of the third dimension to account for. And this is where my previous definition of space perhaps falls short. Because space, although it would be incorrect to say that it's three-dimensional, it exists in reference to three-dimensional objects. So there has to be some way to communicate that. So now, here's the two, if it were two squares, there'd be a certain distance between the two squares, and that would be what I would call space. But now there's a third dimension. There's a depth to that there's a depth to those spaces, and when we're traveling the inner line, we're traveling from bottom to the top, or top to the bottom, we're traveling the edge of the square that faces the edge of the other square. we have not only to account for, or to talk about the distance from the top to the bottom, but now what they call space exists in the third dimension, along those lines, along those edges. Now, can I say that space is simply distance? Maybe I can't. Although I could argue that it's just infinite points. In other words, you're just going to take the distance from an imaginary point to an imaginary point, and then you're just going to move it over an infinitely small increment, and then measure that, and then move it over an infinitely small increment. Keep moving it, and whatever. If I do fail, if my definition does fail in that case, I want to propose another model, and I do believe even the most top scientists would agree that I'm correct in this. And this is, here it is. This is the next model. This is the one model of a universe where my definition would be true, I believe. I want you to imagine that it were two spheres. That's right, not that it ever would be true, but just imagine if what they call the universe was simply two spheres, a certain distance from each other. This is really slippery stuff. Because now you not only have the third dimension to deal with, you've got a three-dimensional circle. And what this means, and I don't know if I'm going to be able to communicate this, but this is the only instance where space would be simply distance. If it were a two-dimensional circle, it would simply be a shape with it would be two shapes with an ever-changing distance between them. But as soon as you make that two spheres, the distance between them not only changes at an infinite amount of points up and down the inner edges that face each other. If you flip it around and go in the other direction, the same is true. The same is true. It is ever changing. Imagine a dot. Now imagine the dot moving in a line. As it moves, let's say it not only moves on a straight course, it also makes